So, now we're going to start talking about the standard template library. Okay? And so we've started to see some of the standard template library already with strings. We've also started to see some of it with, for argument back here, the standard to upper. Okay? And we're passing in some sort of type. Okay? The standard template library is a collection of resources and a collection of functions that allow us just to automatically do things. Okay? And generally, these things are generic. That means that they can operate over a whole lot of different types. Okay? But at the same time, we've just spent the last half hour talking about types and casting and arrays and things like that. And we see that things can't just easily change type unless we know how to change the type. Okay? And so the example we've got on the slide is we've got two functions there that calculate the minimum, one of an int and one of a double. Okay? And if we wanted this minimum function, we need one of these for every single type available that could be used to calculate the minimum. Okay? Now it's going to require a lot of code, and it's also, again, going to get very confusing working out which one gets called when. Okay? So function templates allow us to define and declare one function that can handle different types. And now weeks 6 and 7, we're going to spend 2 weeks talking about all the different types of function templates that we can have and all the things that we can do with them. Assignment 3, you're going to be making quite a complex set of function templates. Okay? But just for now, just stick this in the back of your mind. This is roughly what the very basics of a function template look like. Okay? You declare template, give it a type name. Okay, so the type name doesn't have to be an int or a float or whatever. You just say type name t. Okay? At that point, you can say t min takes in a t and returns whatever they are less than each other. Okay? That's fine. And so that previous slide there, whereabouts we have the two functions, at compile time, this template gets built out into those two different functions automatically for you by the compiler. Okay? So the template, as you can imagine the template is, it's a set of instructions for the compiler to know how to automatically generate varying different types of functions for you automatically. Okay? Just because we have the template there doesn't mean actually we have one function. What it means is we only write that function once. At compile time, because we're calling, say, min12 and min 1.12.2, at compile time, that gets converted into two different functions automatically. Okay? So let's talk about the STL. Okay? So the standard template library contains a number of containers, so sequence containers and associative containers. It contains iterators, and it contains generic algorithms. Okay? And as I mentioned, from week 5, we will be talking about how to write your own versions of a whole lot of these things. Okay? And so the architecture looks a bit like this. Say you've got two containers. They can be different containers. You can pass those containers into an algorithm via an iterator. And from that algorithm, it might return an iterator, and we can iterate over the result of the algorithm and pump it back into another container. Okay? So we have, for argument's sake, J algorithms and K containers. And that means there's a lot of implementations of things. Okay? But all the containers and algorithms are templates. Okay? So they work for however many types that you want. Okay? And they're basically built as generics, or also what I'd say is type agnostic, which means that, for argument's sake, algorithms can manipulate data, but don't care about what container they're working under. Okay? They can just manipulate data of any container. Containers store data, but they don't need to care about the algorithms that operate on that. Okay? And so when we talk about iterators, they're kind of an abstraction away from a pointer or an index. Okay? An iterator means go get that particular element that you're looking at right now, and when you increase the iterator or move the iterator forward or backwards, it knows how to handle it automatically. It's not doing pointer arithmetic, or at least it's not making you do pointer arithmetic. Okay? Algorithms and containers interact through iterators. They talk to each other through iterators. Okay? And each container has its own iterator type. An iterator itself is a type. It's associated with a container. That means that we've got a vector, and we have a vector iterator. We have a list, and we have a list iterator. Okay? But these things are all built to be generic. Okay? So we've got an example. Okay? Here's a problem for you to solve. I'll give you about 10 seconds to solve it. Read in a file called numbers.txt. It contains a number of ints. Then print out its minimum, its maximum, for median, for average, for geographic mean of the data. How many lines of code would this take you? You want to guess? How many lines of code might this problem take you? How would you go about solving it? Okay, so everyone's silent because they're probably thinking about how to solve it. Okay, so with STL containers, I'll give you the solution. There's the solution in 25 lines of code. Okay. Now, I don't, again, expect you to understand all these lines of code just like that. Okay. But as you can see, first of all, there's a whole lot of hash includes at the top. So the standard template library is split out into lots and lots and lots of different containers and algorithms and things that you can do. Okay. So there's 8 different includes up there. We then have a vector on line 11. Okay. We have a file input stream on line 12. This is all coming from a standard template library. On line 13, okay, I'm going to use mouse. On line 13, we use an algorithm called copy. We use an input stream iterator, okay, and we use what's called a back insert operator, okay. And see how it's taking V over here? It's taking a vector. So we are copying all the numbers from that file into a vector, like that, one line of code. Okay? Now that standard copy algorithm is going to be a lot faster than you writing a for loop or a while loop to go and do that. Okay? We're then sorting the numbers from beginning to end, just like that, doing a thing called standard sort. And then we can find the min-max of that collection just by saying what's the front and what's the back of the vector. We can work out what's the median by getting the middle point of the container, by getting the iterator at the beginning, increasing the iterator by half the size of the container. So find the midpoint just like that. Okay? We can calculate for average. Okay, this accumulate should have the standard in front of it. Okay, but we can count for average just by counting up everything as we go along and dividing that by the size. Okay, and I cannot be bothered to explain the geographic mean, but you can do that very simply. Okay, so that problem we had there of how do you go do that, there is a solution, all using the standard template library. Okay. Now, admittedly, I didn't even write this solution. The lecturer from a couple of years ago did. And I don't know if they wrote it or if they got it from a textbook or something like that. But the point here is the standard template library is very, very, very powerful. And so there's lots of stuff that before you would have gone and coded yourself. Here it is all coded up for you. You just need to know how to use it. Okay, so we've got a second problem. Okay? Write a program that outputs the words and the number of times it occurs in each file. Okay, sorted by words. So basically, we just want a tally of all the words in the file and the number of times that they appear in it. Okay, so we've got 2 containers on line 8 and line 9. We've got a vector and we have a map. Okay, we've got a file stream on line 11. Again, we read the entire file into the vector in line 12 and 13. We then iterate over the entire collection in line 15. And just create some counts at this point. And then on line 20, we print it out. Okay, don't necessarily worry about understanding all this at this point, but just understand that you've got these examples of how the standard template library works. Okay, I don't have these ones set up to show you, but I'll get to some more in a minute. Okay, so the design behind the standard template library, okay? We have an arbitrary number of types. So we've got I number of types. We have J number of containers. We have K number of algorithms to operate on those containers, okay? If we didn't have templates, this would require I times J times K number of implementations of function overloads to code, okay? The standard template library attempts to solve this by just using J containers and K algorithms and making it completely type agnostic, okay? Now, the reason why it doesn't say it is completely type agnostic is, as we'll see in a few slides' time, there is some problems, okay? And you should understand where the problems are and know how to get around them, okay? So, the C++ standard template library is the heart of C++, okay? It contains many, many, many containers, and they've also been updated for C++ 11. Okay? Contains over 100 algorithms for doing stuff on the containers. Okay? And it's a really good example of generic programming. And by the end of this course, okay, we'll actually, again, in about week 7, 8, 9, or 10, I'm going to show you the source code for a thing called unique pointer. Okay, it's a template. I'm going to show you the source code for that, and you will, be, at that point, be able to understand how that source code works. Okay? So all components of the standard template library are templates. Okay? And for efficiency reasons, the standard template library is not object-oriented. Okay? So it doesn't use inheritance, it doesn't use virtual functions. Again, we'll worry about inheritance and virtual functions later on in the course. Okay? But you can keep in the back of your mind that STL is not object-oriented. Okay? So I think I have this one as an example. Let's take a look. Or I don't. Oh, no, there's string container.cpp. Opens. There it goes. Okay. So we talked about strings earlier today. The string itself can be a container. Here, what I have is I have a vector of 3 ints, 3, 2, 1. I have a single string called string. Okay. Oops, I'm using the wrong mouse. I can sort my vector from beginning to end. I can copy my vector to the ostream iterator. Okay. The ostream iterator just prints the stuff out to the screen. Okay. Well, because it's been passed in standard cout. Okay. I can do exactly the same code on my string. I can sort my string from beginning to end. I can print it out, character by character. Okay? And it thinks it's a container because the STL does not say string's not a container. So I can pass the string into an algorithm, use the string iterator to glue between them, and they work the same. Okay? So I'm just going to make this, make string container.cpp. Okay, so it's made. Okay, let's take a look at it. There you go. So my 321 vector got converted into 123. My string, string, got converted into ginrst because it got sorted. Okay? That code did that. Okay? People clear about this at this point? Again, you don't have to be clear about how all these things like ostream iterators and stuff work. Okay? You just need to understand the general idea of how these things plug together and that output. Okay? So, why should you use the STL? Well, you don't need to reinvent the wheel for everything you're doing. There's lots of stuff already defined there. It's efficient and it's fast. Okay? So the C++ compiler is optimized to use the C++ library code. Okay? It's hopefully less buggy than your code. Hopefully it makes for readable code. So again, this slide back here, whereabouts we had that code. At this point, this might not be readable to you. Okay? But hopefully, by the end of the course, you'll have a better understanding of how to read that code than just dealing with pointer math everywhere. Okay? Because it's standardized, it means it should be able to operate across lots of different platforms, just like that. Okay? It's a good role model for writing a library. Okay? And it should give you good knowledge of data structures and algorithms and when to use which data structure. Okay? So here is our containers available. Okay? We have 5 sequence containers. We've got a vector. Okay, think of that as just being a dynamic array. We've got a double-ended queue. Okay? We have a C++11 style array. We have a list, which is doubly linked. We then have a forward list, which is only single linked. So it's just a standard forward linked list. Okay? We have some adapters, which is a stack, a queue, a priority queue. Okay? So the stack, last in, first off, a queue, first in, first out. And you've got a priority queue, which is ordering by some sort of priority. You've got a set of associative containers. That means you've got a set, and a set just means that there can only be one of each particular value of something. Okay? You have a map, which is mapping keys to values. In some languages, that gets called a dictionary. You then have a multi-set and a multi-map. Okay? A multi-set, you can have duplicates of things. Okay? Multi-map, the same thing. You then have, in C++11, a whole ton of these unordered associated containers. Okay? Unordered set, unordered map, unordered multi-set, unordered multi-map. Again, you don't necessarily need to know the implementation details of every single one of these, but you should know what these different containers exist and when to use which one. So what can the containers do? Okay? Well, they can be copied, they can be moved, and they can be assigned to. Okay? So, up the top, we have 2 different versions of constructing a vector. Okay? The top line there, vector int v151, says create a vector of ints containing 5 things and initialize those 5 things all to value 1. Okay? The second line says create me a second vector called v2 and copy or move everything from v1 to v2. In this case, it's going to be a copy. Okay? We're going to talk about moving as well in a few weeks. Okay? In the third line up there, v2 is equal to v3. Okay? What happens at this point is the previous value of v2 might be freed from memory. Okay? And then whatever's in v3 is either copied or moved across there. Okay? We're dealing with vectors at this point, so this is all copying, but there is some containers and there's some ways in which we can move stuff. Okay? And we're going to look at copy control next week. Okay? Often we rely on the less than operator to be defined for container elements. The reason why we need the less than operator defined is when we're doing sorting, we need to know if something's less than something else. When we're doing a priority queue, we need to know which comes before something else. Okay? So you often need to define the less than operator. Okay? Actually, I'll say it right here. There will be a question in your exam to do with defining the less than operator. Okay? So if you want to take notes now, there will be a question in your exam about the less than operator. Okay? Retraversing for the same container yields the same order. What that means is going over the same container twice will get you the same order, provided that you use the same iterator and provided you don't add or delete elements between going over the same container. Okay? You should be aware that containers are not safe, but they check for every possible error. If you go and do a dumb thing, that will let you. Okay? So basically, you should obey the requirements and the rules of how to use particular containers. Okay? Violating these requirements, so e.g., using an invalid index, so we've got a vector of 5 there. If we try to ask for element 6, hey, we did a dumb thing. Okay? It may or may not let us, and that's why it results in undefined behavior. It can depend on your compiler whether it lets you do a dumb thing or not. Okay? So, in terms of operations or algorithms, in principle, all operations should be supported by all containers, okay? But that's not strictly true, and we'll explain why in a few minutes, okay? But also, different operations have different time and space complexities, okay? Such as the difference between a vector and a list. Deleting from the middle of a vector can be quite time consuming because you've got to shift all the other elements down around it. Deleting from the middle of a list should be quite straightforward because you just delete that element out and plug back together your pointers between the previous and the next element. Okay? So when you decide which container to use, you should consider how you're going to use it, what operations, what algorithms you're going to use, and how often each operation will be performed. Okay? Again, at the very early design stage, you might not know. So you might design something with a vector, and then you realize, oh, you need a list for that. Okay? The STL should be designed in such a way, you just go change that vector to a list, and everything else in your code keeps on working. Should be. Don't guarantee it. Should be. Okay? So here's a table. Sorry, this isn't an exam. I'm not going to ask you to write this out. Okay? But here's a table of efficiency guarantees for operations on vector, list, and queue. Okay? So constructing them, they all take the same amount of time to construct. Getting the size of them, you can probably see on line 2 up there, getting the size of a list requires us to actually, it requires order in time. It actually has to go through the entire list and find the end of it to get the size. Getting the index at a certain point, for vector it works and for queue it works, for list is not defined for. Okay? Seeing if something's equal to the other thing, hey, they have the same amount of time because it has to go through every single element. Remember before we were talking about at. You should be using at rather than the square brackets to see if something is at some location, because the at guarantees that you won't go off the end of your container. Okay? But again, for list, that's not supported. Getting the size, that's okay. Notice that there's 2 different size functions. There's container size and size down here. Okay? There's a resize operator, but that doesn't exist on list. There's a capacity, but that doesn't exist on these things because capacity for a list doesn't make sense unless you've got a bounded list. Okay? And you have a whole lot of different stuff. Okay? So be aware of which one to use, and you can use these tables. You can go find these tables in the textbook to work out which container you should use when and why. Okay? So let's talk about size a little bit more. Size in a vector is order 1. Okay? v.size in this for loop, okay? When every time through this for loop, when it calls v.size, okay, it just knows what the size is because the vector it's similar to an array. It just knows where its maximum size is. On a forward list, size is not provided. Okay, so on a singly linked list, the .size operator is not supported. Okay. There's a link there, you can go read, it's the whole standard, okay, for a forward list. They have a whole rationale behind it. And basically it's performance. A forward list should be fast. Okay, so the forward list is designed to be very, very fast. And for that reason, they just went, well, we're not giving you the size. You shouldn't need to know the size. Okay?